Okay, this is the fifth lecture. We will talk about testing in general and JUnit testing in particular. Do you know what JUnit is?
It is for automatic testing of the program.
Yeah, you can write in Java your own test program that tests other code, and then you can run all the tests and you will get a display of it. We will take a look at it. But in general, testing is the process of executing a program with the intent of finding errors. That means we are running our program and the only purpose of running it is to try to find errors in it. I will talk about testing in general a bit in the beginning, but then we will focus on this tool called JUnit. And this is the major topic in this lecture. But first of all, often when we talk about different types of testing, we are using words relating to an object-oriented system. We are talking about the whole system, subsystem, components, and a component often contains a number of classes. So this is our hierarchy. We have a system, subsystem, components, and classes. Also, when do testing take place? I have here a simple sketch showing the development process. This is a typical so-called top-down approach. We start with the requirement specification, go to system specification. We are implementing the system and we are maintaining the system. So usually when you're developing a larger piece of software, you go through these steps. Requirement specification, collect features as seen by clients and users. We are here to develop a banking system, then we go to the bank, of course, and ask them what properties do you want in your new system. So we interview a lot of people that will be using this system in the future, and we collect features that they say that this must work. So this is the requirement specification. Then we translate this one into a system specification. This one contains things it's not made up by computer scientists. It's the people who are working in the bank. But we take this requirement specification and say, okay, in order to fulfill this one, we must have a GUI, we must have a database, we must have. So we are translating the wish list from our clients to a concrete specification saying that in order to fulfill all these things, we need this thing. So this is our version of the system of specification. Then we start the design phase, and design is basically modularization. We identify that in order to fix all these things, we need to have a database, a GUI. We are dividing our system into a few components or subsystems. Then we are dividing it even further. We take one subsystem and say that, okay, in order to implement this subsystem, we need a number of classes and components. This is the final design phase. Then we are starting the implementation. We are implementing it, and then the sixth phase here is maintenance. For a larger system, where do we spend most time? We are developing a large system for the academic system here, our administrative system that we keep track of all the students, LADOC. If we should develop this system, we will go through all these phases, but which one is the most time-consuming? Yeah, maintenance. It turns out that the maintenance is... when 10 years later, when we are terminating this system and saying it's too old, if we then should have measured where did we put down most time, it would be in this one, because it takes a year or two to produce the system, but then for 8 years we are updating it and fixing it and adding things to it. So actually, this one turns out to be more and more important. 30 years ago, they thought that once we had the system up and running, it should work forever. But now we have realized that we are adding new things to systems all the time. They are not a constant factor. They are evolving all the time, the system. And also, we are talking about software decay. Initially, our system had a very nice design. We had separate components here interacting in a nice way, but then we start to add new features to it. We are adding new things, and our initial design is vanished. In the end, it's a mess. Then we say, after 10 years roughly, saying that we cannot go on with this anymore. We need to restart from scratch. So the end of a software system nowadays is often that each new feature that we add is so complex. It takes so much time to add even a simple thing that we decide that we should restart again. Anyway, that was short about the software development process. Different phases in the software development process requires different types of testing. The simplest and the most commonly used approach is component or unit testing. This is done by the programmers themselves. They are producing some kind of component and then they are testing it to make sure that this component, it works. It can be a graph implementation. I have implemented a graph and I'm testing and this one works, and then I give it away to someone else to use it. Integration testing is when we are putting together different components in subsystem to a larger piece. Then we see that they are working together. They have been developed independent, but now we are putting them together to see that, okay, they fit in some way. Alpha and beta testing, also called release and acceptance testing. This is test of the whole system that takes place in our company before we have given it away to the customers. And then the beta testing is that we are giving away our software to the customers, but it's not online yet, but we are testing it with the customers and the secretaries or whoever that will use the system. This is the final phase before release. Then we have something called regression testing. We are adding a new feature to our system, then we must test all parts of it or certain parts of it to make sure that this new feature doesn't ruin anything, other properties. And performance testing to verify that it's stable and that it is not slow enough, or not too slow and not too memory consuming. So different phases in the software development process requires different type of testing. Independent black and white box testing is also frequently used words. Independent testing. You are developing the code and you test his code. What is the advantage with this approach compared to that you are testing your own code?
I can do a test.
What?
If I do all the things, maybe I can cheat.
Yeah, you can cheat, but and also I wouldn't say that the programmers are cheating. Most of them are not, but you're trapped in a way of thinking. It turns out that you have a tendency to test things that you already have implemented. Things that you have forgotten to implement, you also forget to test them in some way also. So we get a better result if we have an independent test team. However, more costly. Once you have developed your code, you can rather easily test it, you know how it works. If you, on the other hand, should test his code, you must read up on the code and try to understand how it works. So it takes a bit more time, but it gives better quality. What is black box testing? Well, we consider the code as a black box. We don't know what's inside it. We only see a box here with a certain interface, and the interface is maybe methods. So we are only testing the methods to see that they are working. We are adding in a list and it gets sorted, and we see that sorting is okay. We have no idea what goes on inside. We are just checking the interface to see that the method is delivering. This is of course simpler. We don't need to know anything about the code. The disadvantage here is that it might be that certain parts of the code are never tested. It might be an if statement that is never become true. So the code, everything that takes place inside the if statement, our tests never reach this part of the code. If you don't see the code, then you cannot make sure that every part of the code is tested. The contrast is white box testing. This is the programmer himself. He knows everything about the code. He can make sure that his test is touching every piece of the system. So when you are designing your test, looking into the code to make sure that every piece of or every statement is tested, then it's white box testing. When you are not looking into the code, only test the methods to see that the result that comes out is okay, then it's black box testing. Test interpretation. Testing can only show the presence of error, not their absence. This is rather depressing. It says that no matter how much we test, we can never be sure and say this one works in all cases. And it's easy to understand. We have an infinite set of possible input data, an infinite set of possible user scenarios. So in general, we cannot test all possible executions. That means we cannot guarantee that there is no errors in here. We are testing, runs a number of tests, but we can never say that I am sure that we don't have any errors in this code. We can do it, but only in a few cases. So this is rather depressing. Why do we then do testing? If I cannot guarantee that my code is error-free, why do I test? Yeah, reduce the possibilities, but basically build confidence in the software. When you have developed a piece of a method yourself, you are testing it, and after a while actually you start to believe that this one works. You have tested it enough that you start to believe that this one works. And this is basically the basic idea with testing. We would like to at least start to believe that probably there is no error in this one. We believe that this one will work. Then we are done. We cannot prove it, but we can actually, for ourselves, say that it is not likely that this piece of code comes with any error. I have tested it thoroughly and I believe in it. Then you're done with your testing. Reason for testing. Well, we will detect certain errors, and of course we would like to see if the system crashes. It shouldn't crash our system. That's of course. It shouldn't do incorrect computations. Are we adding 5 with 3? The result should be 8. Nothing else. Data corruption. What is this? What do I mean by a possible error could be that is data corruption?
Maybe when accessing an element, you shouldn't change, it is changing?
Yeah. For example, I'm accessing a database. I say, give me all the students in this course. Then I should get all the students in this course, but I shouldn't change anything in the database. So it might happen that you unintentionally change the data in a way. You don't want to do it, but an effect of asking for something might be that the data is changed. Then we have data corruption. And also, we would like to verify that the system meets its requirements. We have often, when you are being given a task by your boss, your first job as a programmer, you should develop this piece of system. He has given you a list of requirements. You should verify that these requirements works. In your test, you should check that everything he said that your system should manage, it also manages in this way. So we test also to verify that it does its job. When should testing take place? The old-fashioned approach is that first we develop the system and then we test the system. It turns out to be very costly. They develop the system for 1 year and then the test team say it's not working. Go back and redo it all from scratch. Nowadays, everyone says that it should be an integrated part of the development process. Once you have a piece of software completed, you should test it. You should test it as soon as possible. And then you put them together and then you test them one more time. So this one, in this one, you remember my software development process. Then we had of implementation, and then we had testing as a separate block after the implementation. It is now considered as hopeless. I'm writing here, still popular among students. Every year I have students that 2 hours before the deadline, they say, I just realized that my system is not working. And then they give me a code to me, pointing out that it's not working. Then they haven't done enough testing. They have waited with testing their system until it was 2 hours before the deadline. And we failed them. I will talk about this one. It sounds strange. Before implementation. I will show later on what they are talking about this case. Test case design. What do you need to test something? Well, I have some kind of an algorithm here. Identify a set of features which, if successfully tested, can verify or indicate that the requirements are fulfilled. For each feature, find input that tests different aspects of this feature, find corresponding output that verifies a correct behavior. A triple feature, input and output is called a test plan for this feature. It might sound a bit abstract, but assume we have a method called plus. Int A, int B. It returns, of course, A plus B. You should test that this one works. What is needed?
You should above that. You should above it.
You should have a number of input. That's. We should have a number of pairs in this case, A, B, that tests that this one works. But just as important as this one is that we should also know the result. Yeah. So in order to test this one, we should have a number of things that looks like 7, 3 goes to 10. The point here is that in order to check that something works, we should not only test it with a number of input, we must also know what is the expected result. Otherwise the test is useless. If I'm running this plus method with 7 and 3, 5 and 6 without checking that the result is correct, it's a waste of time. So what I'm trying to say here is that a feature, it might be just a method in this case. If I would like to check that this method is okay, I need a number of input data and I need a corresponding set of output data. So when you should test your method, you should basically come up with a number of these pairs that you think, if I can make this one works, then I think my method is working. Components and unit testing will be the main topic from now on. A component is something small and self-consistent. It can be a list, it can be what did I have here? An algorithm, or something that can be tested in isolation. It can be one class, it can be 5 classes or something like this. But something that we can consider as one part of system that is not depending on anything else. I can test it in isolation. It's a component. And unit testing is almost always the component developer yourself. In many companies that we have been in contact with here in Växjö, when you as a programmer are submitting code, you have done your code and you're submitting it to the system, then you must also submit the test case. For each thing you are submitting, you should also submit the corresponding test case. So each piece of code has a corresponding test case. And so the component developer, at the same time as that they are developing their component, they are putting together a unit test. It's considered as a part of the system. And the goal is, of course, to convince ourselves that the component is working properly in isolation. And this should be done during or directly after implementation. You have been assigned a task from your boss to do something, you do it and you test it right away, or while you are developing it. Here I have an example. Assume a method, sort, that takes an array of integers. And your task is to test this, that it works. Exhaustive testing, test all possible cases. Well, it's impossible. There is an infinite number of different arrays. So how many tests do you need?
We should consider the range of them that cover almost all of them. For example,
yeah, but the range might change. The length of the array can be anything from 2 up to 2 million.
No. If it works, for example, for 20 type of test,
yeah.
We could say almost it will work for all of them. Not absolutely, but
yeah. I totally agree that if it works for 5 standard cases, then it usually works for many standard cases. But apart from standard cases, you should also look at what we call extreme cases. It turns out that I'm asking you to implement this one, you do it, but then I give you an array of 0 length. It might be that you haven't thought about this case. You are trying to pick out the first element or something like this from it. So it will not work. So the basic idea is that you should have a number of standard cases, but you should also have a few test the extreme cases. It turns out that most errors are actually in extreme cases like this. The guy who is implementing them have forgotten to think about the case where the array is of 0 size or just size 1. So test all extreme cases, test a few standard cases, and maybe just for performance issue, test a very large array to see that it doesn't collapse at this time. So I would say something like this. We only need 5 different tests. Maybe 7, maybe 4, but you shouldn't try to impress on someone and make 100 tests. If it works for some standard cases, it probably works for all the other ones as well. So usually testing should be that we are picking clever cases that test different aspects of it, not many cases that test the same thing. Yeah.
I think that in future, if there will be a crash in a case, we could add the 6.
Yeah. Yeah, that's true. The process of testing is not done only once. We are developing something, a sorting array in this case, and we are testing it and we are submitting it to somewhere else. Then they find an error in it. Then we go back to our test case and produce one more test that triggers this error. And then we fix the code, and then it should work one more time. So every time we find new errors in our code, we are extending the test cases to make sure that we will not miss this case in the future as well. So this is called fixture, this one, the number of input data and the corresponding result. The basic idea is to test all extreme cases, odd cases that easy for a programmer to have forgotten. Test a few but not many standard cases. Test scalability by a large case. In the sorting case, we might have an array of size 5 million or something like this, just to see that it doesn't collapse or something like this. Of course, there is a get method. There is no large cases for a get method. it should only return one value. So this idea of using a large case only works for certain methods. White box testing. You should at least test every method. If your class have 10 methods, all of them should have been tested. Preferably, you should make sure that every statement is tested in your code. You have an if branch, if x larger than 0, then we do something. Otherwise, you should of course write tests that hits both of these branches in the if statement. If something generates an exception, you should of course have one test case that generates the exception to see that the exception generation works as well. Yeah. So the literature and what I is actually recommending is that you implement one method and then you test this method. But I think you're already doing this in some way, maybe without thinking of it. We are asking you to implement a class, you're implementing one method, then you have some piece of code that you test it to see that it works. Yeah, so you are basically doing this. You are adding one method at a time and you do a bit of testing to demonstrate. This is just one way of formalizing this approach. I guess in your case you might remove this test code when you start with the next method. You shouldn't. You should let your test code only grow and grow all the time. So implement a method and test the method. There is one approach to testing that is called extreme programming. They are suggesting that we should write a test for M, then implement M, and then test it. You should start by thinking in terms of tests. You do a test, and then you implement the method that fulfills this test. They are saying that you become more goal-directed. Once you have a test, all you have to do is to implement something that fulfills this test. Then you're done. So people say that this is a good idea. Non-believers say, yes, it only works. It is nice for smaller projects. It doesn't work for more complex systems. But in general, I am recommending this approach. I think that no matter whether you are using JUnit or some other test tool, you should implement one method at a time. You should test to see that it works before you proceed with the next one. You should, because in the next one you are maybe using the previous method and things like this. So take small steps, make sure that the code is working before you go to the next feature or whatever you're interested in. How about a break? Let's do only a 5-minute break, so let's be back here in 5 minutes from now, okay? Okay, let's move on. Could you please open the door for him? The remaining part of this lecture, we will talk about a tool called JUnit. It is a tool designed to help you write testing Java components. It is for free. It is easy to download, and you can find plenty of information about it. It's a rather small program. If you should look at the code for it, you will see that it's only 20 classes. It's available in other languages, and it's supported by Eclipse. I had an idea that I should. Once you have, here I have a test program written for JUnit testing, and the thing is that Eclipse recognizes this as a test program. So all you have to do to run it is just right click on it, go run as JUnit test. And then it will show that we have run 2 tests and both of them passed here. So 2 out of 2 tests was okay in this case. And if you should have some errors here, it would present the errors in this case. Yes?
Does we have like a code coverage of the main method we're testing?
Do we have?
Like a code coverage of the method testing? No?
Code coverage.
Yeah, it's like when you get all the code inside the method, and you just say like, okay, you passed here, but you didn't test this part of the code.
No, I think there are other tools that can run a test and then in some way, yes, point out that the test we were running now, it covers this part of the code, but it didn't test this part and this part. But I don't think it is available in JUnit. So I will show on slides now a number of examples using JUnit, but I just would like to show you that it's very easy to run in Eclipse. You write them just as ordinary Java programs, but rather than run them as a Java application, you run them as a JUnit test. It displays the result here on the left-hand side. Oh. I think this is a good tool. Very useful, easy to get started using. You will see that it's a bit difficult to understand it in detail how it works. The first time I saw it, I was scratching my head and said, okay, it works, but how do they do it? I will try to explain how they do it, but you don't need to know it. You should know how to use it, and it's easy to use. My first example would be a test program that tests this simple method. I have a method here that just computes the multiplication a times b, but I do it in a bit strange way. I do it using recursion. So if b equals 0, then I know that the result is 0. We're multiplying a with b. If b is 0, then the result is 0. Otherwise, I'm saying that the result is a plus a multiplied with b minus 1. Does it make sense? I'm saying that a times b equals a plus a times b minus 1. This is a recursive approach. I solve the problem by using a smaller problem. So mult a times b will call mult a times b minus 1, and it will call with smaller and smaller b's until it reaches this case where it stops and returns 0. So it's a strange way of computing a times b, but it works. And the only problem is that the second argument b must be non-negative. So I start by checking if b is negative, then I throw an exception. Otherwise we have the so-called base case. B equals 0, I return 0, otherwise I return the result of this computation. Yeah, it's a simple method. How should we test it? Well, my idea is that we should test the extreme cases. 0.5 multiplication with 0 and 1. We should test a few standard cases, and we should test a large case. And we should make sure that an exception is generated when the second argument is -1. This is my starting point. If it works for this one, I actually think it works for all the other cases. So then you have your JUnit test, and this is my test method that is testing the multiply method. We are using a number of predefined assert methods. These are the actual tests. I am assuming that 0 should be equal to 10 multiplied by 0. I do the computation here and I know the result. I know that this one should give 10 and this one should give 0. When we are running this code, this will be the tests, and if they all pass, it will be green. If one of them fail, it will be reported that you were doing this thing, you thought it should be 10, but it turned out to be 11. It will report something like this. So we are using methods from the JUnit library up here, and you are writing one test method for each method you are testing, or you have one test method when you are testing two methods. In our case, I have one test method here testing the multiply method. These were my extreme cases. I test a few standard cases, and I test a case with a large number. I'm computing this one, and I'm verifying that it will be this number. And also, I'm forcing an exception here. In the final part of it, I do something which is illegal. My second argument was -1. And I have up here said that I expect this method to generate an exception. So if this operation didn't generate an exception, we will have an error in our test code as well. Yeah. So this is basically what it looks like. It is an ordinary Java class, but it contains a bit of strange annotations, and we are using these assert methods. But it is an ordinary Java program. You are writing one method for each thing you are testing, and then you are just running it as a JUnit test. And it will run all these tests, and if any one of them fails, it will say you have an error at this point. You thought it should be 10, it was 11. You thought it should be 50, but it turned out to be something else. When you get back home, these examples are available in Moodle. Run them to see that it works in your Eclipse. Try to change some number here to generate an error as well, to see how the errors are presented also. First of all, we must import a few things. Org JUnit test, this is the code that we are using. This one looks a bit strange. We are we are importing all the static methods in the class assert. That's what we are doing here. These were the ones by this statement up here, we are making these methods available in here. So we are making the assert methods, all methods in assert are we making available with this statement. Each method must be annotated with test. You see here is my Java method where I do my test. You must annotate it in this way. This is the one that tells JUnit that this is a test case. You might have other methods in your class, but they are not a part of the test case. So this annotation will inform JUnit that this is one of the methods that should be tested. We used assert equals method. We are doing a computation here, and we are saying that the result should be 0. So we are verifying that this computation will give the result 0. There is one other version where you can also provide an error message. If this one fails, if 10 multiplied with 5 didn't equal 50, it would also print this message. It will point out it was this assertion at this line that failed, but it will also say this message. You can provide a bit of information as well. So far we have only used assert equals, that this number should be the same as this number. There are many other assert methods, assert true, assert false, where you can do different assertions. Here is another case. We are back to sorting arrays. I have done a simple sorting method here. I'm using an algorithm called selection sort, but anyway, it's actually not that important. The input is an array, and this array will be updated. I will sort it. So we should test whether it works or not, and then my idea is that we test with an empty array, we test with a singleton array, we test with a few standard cases, and in the end we test with a large array. If it works for all these cases, we think that this algorithm is actually correct. So this is my corresponding test method. I didn't have space now, so dropping all the small tests. I'm creating an array of size 1, I'm sorting it, and I make sure that it's not changed. I have a number of such tests. Take a look at the code in the Moodle. But down here I start to use help methods. Quite often when you do testing, you need, rather than adding arrays with 100 elements, you come up with some help methods that lets you in an easy way generate test data. So in this case, I have implemented a method called random here that generates an array of this size containing elements from 0 up to max, and it returns an array with this content. And this one is suitable for testing my sorting routine. So up here, I'm generating an array which is of size 100 containing elements between 1 and 100. So a random array of size 100. I sort it, and then I check that it is actually sorted. That means I go through all the elements from the first position to the second to last position, and I compare that the one before is always smaller than the one afterwards. So after sorting we have an array which is sorted. That means that this element should be smaller than this element, and this element should be smaller than this element. And this is what I do here. I generate the random array, I sort it, and I verify down here that they are actually sorted. I do the same thing. This time I'm using a much larger array. We have 100,000 elements in the range from 0 to 1 million. And I'm sorting it. It takes about 15 seconds on my computer to sort them, so it stops for a while, but then it goes on and it checks that it works. The idea is that once you start to write your test, you will after a while get bored by constructing arbitrary arrays and things like this. Then you should generate help methods like this. You write a method that generates test data for you. This is not the part of the test. It's not annotated with test. It's just something that you do to speed up your testing. The assert classes, we have used assert equals. It actually uses the equals method that we talked about yesterday. If you're saying that this one should be equal to this one, inside the code they will use this method to verify that they are equal. There is something which is quite similar, it's assert same. Then we are using this one. We are checking that it's the same object, not that they are equal. Assert true, assert false, assert null, assert not null. There are a number of these methods, but this one is the most frequently used. You do a computation and you check with the result to see that they are A equal. I will only show a few more examples, but with this lecture I have a larger test case. I have an interface that looks like this, intlist, and I have provided one class, intlist imp, that implements this one. And I provided a test case that tests all these methods for the list. It is a rather larger Java test class that contains 5 or 6 different test methods that tests all these properties of this one. So this is the example that I would like you to take a look at after the lecture or before you start to do your own tests. My code, the test class, it contains all the separate tests, test constructor and size, test add and get, test index of test remove. I have, 6 different test methods here. I have also a method called set up and tear down. They are annotated with before, and this one is annotated with after. You will see that when you are running this test case, it will execute before, and then it will take this one, the first test, and then it takes this one. And then it takes before one more time, the next method, and after. So this one is used to create, if you want to build up something before you do the test, you do it in before. And after here is used to tear down, remove things before the next test. So there are different annotations that are basically defining in which order things should be tested. So the algorithm used is that JUnit identifies methods tagged with before clause and executes it. If you don't have any such method, you're not using this annotation, it will not happen anything. JUnit identifies methods tagged with before and after. In my case, it was set up and tear down. They identify all methods annotated with test. I have a number of these methods in my example. And then for each test method, they are running set up, test, tear down, set up, test, tear down. So by annotating them, you are saying that this is the before says this is the method that should be run before every test. After says that this is the method that should be run after each test. And then they go through all the tests and call set up, test, tear down like this. And you can also have one method tagged with after class. It will be the final thing. Before the test stops, they will run this after class method. I have, if you're interested in how it works, I have put together a class called JUnit demo. It contains all possible methods, all possible annotations, but they're just printing some information. But if you're running this code, you will see in which order the different methods are executed. It will print before class, and then it will print set up, test method 1, tear down, set up, test method 2, tear down in a certain order. They are using 2 rather advanced Java features, annotations. You have seen annotations in the previous lecture. What annotation did I recommend you to use? Override. That was an instruction to the compiler. In this case, this annotation is an instruction to the JUnit test program. Annotations are one way to tag your source code with different information. It is often, it doesn't have any effect on your execution. It is a annotation for other tools to use. This one was an instruction to the compiler. Test is an instruction to the JUnit. So these are annotations. Reflection. You can write Java programs that are analyzing another class. You can write a program that says, okay, give me this class, and then, okay, give me all the methods in this class. And then we can execute all the methods in this class. This process of that Java can analyze a class at runtime. One program can analyze other programs. It's called reflection. And they are using it all the time in in the JUnit. They are taking your test class and they are saying, okay, give me all the methods annotated with test. And then they start to execute them in a certain order, these methods. So they are using reflection to do the actual, when they are running the test. This is just one example. I'm testing add and get. Once again, I have constructed a help method build. Build 5, it constructs a list that looks like this. And then I'm checking if the size of it is 5. Often testing is a rather trivial thing. You should test that the size method works. You build a list containing 5 elements, you ask it what is your size, and you should verify that it actually is 5. We are using get, and we know that the list contains 0, 1, 2, and 3, and 4, and what I'm doing down here is that I'm picking out the elements and comparing them with what I expect it to be. In the first position, I expect it to be 0. In the second position, I expect it to be 1, and so forth. We are just testing that everything works as it should. Did you have a question?
Yes. Can we do, because you said execute test after test?
Yeah.
Can we do like parallel tests now?
Well, JUnit is running them as a sequence. Okay. If you like to, you can come up with your own parallel JUnit that runs all the tests in parallel. But running the test usually takes no time. So we are not in any hurry at all. Here I am checking exceptions. I start by saying that the result is false. That's my initial idea. And then I make an illegal access here to the -12th element. This will generate an exception. So I'm catching the exception and I'm saying that result is now true. And if this one is generating an exception, this one should be true. So I'm asserting down here that it is true. This is simple code to verify that get -12 is generating an exception.
We could expect it, right?
Yeah. As I said down here, see slide 18 for an alternative approach. We could have up here said that and then we could have just used this statement.
I think that it is more without maybe.
Well, the problem with the other approach is that after this, you cannot have any other tests. You can only throw exceptions once. Yeah, but both are okay. So don't hesitate to make your own help methods to generate data. In my case, I have one called build that generates, depending on the size, it always generates 0, 1, 2, 3, 4, 5. The advantage of this one is that I know exactly what element is in each position. But for testing the sorting, the random was also good. So don't start to do your testing, but when you realize that you have done the same constructing an example 5 times, then you make your own method that generates them automatically. In JUnit, I said it was straightforward. In JUnit, you can just right-click on the test and select Run as JUnit. If you're not using Eclipse, you can start your test from the main method like this. Here I have an ordinary starting point of a Java application, a main method, and there are some classes available in the JUnit library that can help you to run your test. So these 3 lines of code are starting the test of my test.int list class here. So. But if you're using Eclipse, this is far easier. But if you're not using Eclipse, this is the approach to take. Oi. So from now on, when you are developing code, you are adding a method and then you are testing that it works. Why not use JUnit is my idea. JUnit is just as easy as a main method to test that it works. And you can store them and you can reuse these tests later on. So the idea is that you implement a method and then you write a test in your JUnit test. Each test method tests 1 or 2 methods depending on the complexity of the methods. Don't use any exhaustive tests. Test a few standard cases, focus on extreme cases, add more tests on demand when bugs appear. And don't hesitate to create a few help methods to generate input data, like build and random in my example. Go home and get started. I think in the second assignment we give instructions, but it's straightforward. You must download and install a jar file like this. Download my JUnit example and run them in Eclipse. Study how they work, introduce a few errors to see how they handle errors as well, and then start to work on the JUnit exercises. You will be asked to write a JUnit test for your generic queue, for example. Yeah. And there are plenty of readings. If you just Google on JUnit plus whatever, you will find plenty of information. Questions? Okay, go home, do a bit of programming, and I'll see you next week. Bye.